Our next speaker is Leah Bottmer. So, I'll help set up your slides. And Leah is a graduate student in the economics department.
Thank you so much for the introduction. Hi everybody, my name is Leah. I'm a 60 student in the econ department, and I'm excited to present my project Synthetic Control and Disaggregated Data Settings today. I feel a bit self-conscious going after such a cool presentation. My talk is going to be a bit drier, pun intended, but hopefully you're going to get just as excited about synthetic controls as about whales. So yeah, my project builds on the synthetic control estimator, which some of you may not be familiar with, so I'm going to start off with a high-level review of the method. The estimator was introduced by a series of papers by Alberto Abadi and co-authors in the early 2000s and has become a very popular policy evaluation tool ever since then. The main goal behind the method is to estimate the treatment effect of the treated unit. And I'm going to just take one example to kind of explain the intuition behind this estimator, because it actually is a very intuitive estimator. So the authors in one of their papers were interested in estimating the effect of Proposition 99, which is a tobacco control program in California, on California cigarette sales. Now, when they were conducting their analysis, the main issue they went into is that they don't observe California's cigarette sales without Proposition 99 being in place. This is also known as the fundamental problem of causal inference. Now, this is exactly where synthetic control estimator comes in. Based on a selection of donor units, in this case, all of the other states in the United States, the estimator tries to construct a synthetic California that mimics California's cigarette sales in absence of Proposition 99. How exactly does it do that? It picks a convex combination of a subset of the units, so in this case, Montana, Colorado, and South Carolina, to optimize pretreatment fit. So what does this look like on our graph? The dotted vertical line here represents the passage of the law. And pre-treatment, we can see that the synthetic California that we constructed, which is the dashed line, tracks actual California, which is the solid line, really well. And then post-treatment, those two lines diverge, and the difference between these lines is exactly what we attribute to the treatment effect of Proposition 99 on California. Now, one very important step in this estimation procedure was actually finding all of the donor units, so what units should we put in this donor pool. And in this case, it might have seemed pretty natural to just use all of the other states. However, this may not seem so natural anymore if I told you that you also observe each county's cigarette sales. So speaking of sort of, the theme of some of the panels earlier, of trying to make use of all of the data that we have available, my project deals with the question of how should our analysis change if we had access to county-level data instead of state-level data. So here we're thinking about leaving the treatment at the state level as indicated by these two plots. And in general, we can think of this as a broader question as thinking about, well, how can we integrate disaggregated data instead of just aggregated data, where aggregated data would just be any data that's at the same aggregation level at the level at which treatment is assigned, and disaggregated data, any data that is aggregated to a lower level than treatment assignment. So in the extreme case, it could go all the way to individual level data. For the purpose of today, I'm just going to focus on one aspect of this problem, which is disaggregating the control units. So here I'm just going to think about leaving my treated units, so California at the state level, and thinking about trading off between using states as donors, as we are in the left graph, which I did in the original motivating example, versus the state-county one, which uses now counties, so we can pick, probably the control estimator will pick some counties in the states that were picked by a state estimator, but also some other random counties. So I'm going to start by just introducing these two estimators a tiny bit more formally, so some math, yay. So starting off the state-state one, which is just exactly this original estimator that I told you about in the motivating example. The state-state synthetic control estimator estimates the counterfactual California by just a convex combination of all of the other states. So here W is the weight vector, and W is chosen to minimize pretreatment errors subject to the convexity and non-negativity constraints. And now when we're thinking about incorporating the control counties, the estimator takes a very similar form, with the main difference being that now the weight vector is indexed by state counties. So the dimension of the weight vector increases by a lot. But in general, the optimization problem we're doing is still very similar to before. So just the dimension really changes. And the one really interesting observation to make here is that actually it turns out that both these optimization problems are equal if we add an additional constraint to the state-county synthetic control problem, which constrains all of the county weights to be exactly identical to the average weight the state estimator assigns. So they're all equal within a state. Now, how can we trade off between these two estimators? The intuition is that this trade-off is mainly driven by two components in the data. The first one being the signal contained in the data, so the signal contained by the states and the counties, and the noise in the data. So here I'm plotting the signal against the noise in the data. And in the ideal world, the data we like to be using contains a very high signal and ideally no noise. Now, of course, we're not in an ideal world, so we always deal with some of that. So how do our two data sets compare to this? Let me start off the county-level data set. The county-level data set is going to contain quite a bit of signal because we can use the heterogeneity created by the states as well as the counties. But at the same time, it's also going to have quite a bit of noise, especially when we're comparing this to the state-level data, because the state-level data is inherently more noisy since we're kind of averaging out some of the idiosyncrasies by the counties. But at the same time, the state data also contains less signal because we cannot make use of that heterogeneity created by the counties. So now, which of these two data sets we're using basically depends on their position in this graph sort of relative to each other and relative to the ideal world. And that position is going to be driven by the variance of the signal, so the variance of the state component and the county component, as well as the variance of the noise. So let me put some more numbers behind this. And I want to show you some simulation results that I conducted. And here I'm plotting the signal-to-noise ratio of the county-level data on the x-axis against out-of-sample performance measured by root mean squared error, which is normalized by the state-state performance. And let me start off by two extreme scenarios that kind of provide a bit more intuition behind when each of these estimators performs well. So let me start off by the left-hand side, where basically we're in a scenario where our counties don't provide any additional signal. In this case, you'll be expecting the state-state synthetic control estimator to be performing better because basically counties only contain noise, and so the state county won't be overfitting, and this is exactly what we see in the data in the simulations as well. Now, going to the other extreme end of my plot, we're basically in a setting where there's essentially a noiseless data set. We would expect the state county one to be performing better because we want to make use of that extra heterogeneity, especially since it comes basically at no additional cost in terms of noise. And that's exactly what we see in the data as well. So now, quite naturally, given these two flip performances on either end, what happens when we're varying the signal-to-noise ratio, we find that there's a switching point somewhere in between. And the main takeaway from these simulations is that the county-level data is more valuable when its signal-to-noise ratio is high. Now, given these different performances of the two estimators, depending on the strength of the signal-to-noise ratio, you might very well be asking yourself if there's anything we can do better than just restricting ourselves a priori to kind of using either one of these data sets and being sort of somewhere in between. And this is exactly where my proposed estimator comes in. So my paper, I'm proposing the multi-level synthetic control estimator, which augments the state-county synthetic control estimator by a penalization term that penalizes the in-state variation of the weights. Now, this penalization term is motivated by exactly the constraint that makes both the optimization problems, the state-state and the state-county one, equal. So now, as lambda goes to infinity and our penalization term dominates, we're going to get the state-state synthetic control estimator back. And when lambda goes to 0, we're going to get the state-county one back. So it unifies both of these extremes. Now, what happens when lambda is somewhere in between? Let me just summarize this information on a graph right here, where I'm plotting my penalization parameter against the root mean squared error. And so again, when lambda is 0, we're going to get the state county one back. When lambda is infinity, we're going to get the state one back. And here I'm plotting both the total RMSEs to be the same. So essentially at that switching point for my simulations. But for any given data sets, those don't have to be the same. Now, when we're increasing lambda from 0 going to infinity, the bias of the estimator is going to go up because we can make less and less use of that extra heterogeneity. But at the same time, the variance is going to go slowly down because we're going to use the less noisy data and average over more individual components. So given these opposing forces, what happens for the multi-levels in the control estimator, we'd expect it to be below either one of these extremes and hit a minimum somewhere at lambda star that's positive but less than infinity. So let me leave you with a main takeaway of the presentation. I document there's a trade-off between using how much additional information the counties bring into the estimation procedure versus how much additional noise, which results in different relative performances depending on the signal-to-noise ratio. I introduced a multi-level static control estimator whose performance I'm including here using an hierarchical lambda, which unifies both of these and in the ideal world outperforms either one of them. Now, of course, the next step is to get a feasible estimator from this infeasible one. This is where I'm currently working on, and here I'm plotting one heuristic lambda that I've been trying out, which seems to be performing really well. Thank you so much.
Wonderful presentation. It's the first time I see synthetic data used to evaluate healthcare policy. What kind of other healthcare policies can you talk about that are being included in this kind of?
Yeah, thank you so much for the question. There's a lot of different applications. So I think, so I'm working more on the methodological side, so I don't touch a lot of the actual data and more of the simulated data, but I know that mainly it's used to evaluate like policies that include, for example, taxes on alcohol, on nicotine, and stuff like that. So there's those are a lot of applications sort of when we're looking at policy evaluations. I think the estimate is also used a lot in industry, but I can't speak that much to that because I don't really have a lot of experience with that.
Can you please define signal and define noise in the context of your presentation?
Yes, so basically I'm thinking of signal as, basically I'm thinking of the data as being sort of in the like very simplified world constructed by 3 components, which is the state component, that's common to each county within a state, a county component which is county specific, so that creates sort of heterogeneity, and then the noise. And so basically the signal is going to be coming from that state component, which you can think of sort of a bit as a like fixed effect if you're familiar with fixed effects, or like factors on a factor loading model. And so then sort of we're thinking about the variance of each of these components, treating those as random.
Is there a way of learning structure in the noise? Like, is there a way of kind of discovering what it is that's leading to the sources of noise at the county level and being able to kind of use that to then magnify the signal in order to kind of dampen the noise?
Yeah, that's a great question. I actually have not thought about that. So that's definitely a great idea, trying to think about if you can use some of that. I'm hoping that the way that my estimator is sort of trying to make use of some of that county level data, that like that it can sort of learn a bit the structure behind what of the noise is like actually useful noise or like useful information versus like what is just pure noise. But yeah, that's a great suggestion. Thank you.
Okay, thanks. Let's thank Leo.